So let's start by a brief summary of some of the things we saw yesterday, or rather on Friday. And also I want to make a few comments on the homework. So let me just first ask, how many people are actually doing the course, and in particular doing the homework? Okay, almost 70%, more or less. Okay, so how many of you already finished the second part of the homework? Okay, very few. But did you play with it? Did you start working on the second part, half of the homework? Not yet. Some of you. Okay. The first one, yeah. Ah, that was already handed in. Very good. Okay, so let me remind you then about a few things that you have already seen concerning the first homework, because we will encounter it a bit later today and especially tomorrow. So what you were studying in the first homework, you started seeing how operators with spin look like. And the idea was to start, the main part of the homework was to start with a composite operator, something like a product of two fields, phi bar. Okay? So the analogy will be that when we will start considering the fundamental object in a gauge theory, as we emphasized several times already, they are single trace operators. So they are trace of a product of fields. So they are also composite operators. So this is the analog in a very simple theory. So it's important for us to start getting some experience with composite operators. And then we saw that, okay, as soon as we start considering vector operators in this simple free scalar theory, we have two options. Either we just take a derivative of the operator, that gives us a descendant, or the only other option with one derivative is to put a derivative in the middle of the scalars and put a minus sign if it acts on the left or on the right. Okay? So if this guy is the descendant, this one is not, and it can only be this, and indeed you can check that these two guys are orthogonal to each other, they have zero correlation function. And then you go to two derivatives, and of course you have two options. You can either take this means totally symmetrized, because we only consider representations which are totally symmetrized. We can either take two derivatives of the operator, then again it's a descendant, or we take one derivative of this operator. Sorry, what am I doing? This is not a descendant. Or we take one derivative of the guy that is not a descendant, but this is again a descendant. Or we take the remaining combinations. So a priori there are only three combinations. So two we already used. We know they are descendants. So we take whatever is orthogonal to the previous ones, and this gives us an operator with spin 2. And so on. So it's clear that they are uniquely fixed. If you have two fields, you can always, at the next loop order, find the only one which is not orthogonal to all the descendants. And you are encouraged to check that this general formula matches what you expect. So the linear combination, you have some k derivatives acting on the first guy, the remaining ones on the second guy, and there is some square of some binomial coefficients there. If you now take this formula and painfully compute 3-point functions between that guy and two scalars, and also 2-point functions, and then if you were to normalize the 2-point functions to 1 so that from the 3-point functions you read the structure constant, okay? This will be a simple exercise. I do not believe that you were asked to do this, but it will be simple to do it. You compute the 2 and the 3-point function, so just divide one by the other. You will get this formula here, I believe, up to maybe some factors of 2, because I'm quoting it from memory. Okay, so it's something like this. Okay? So we get some factorials, some square roots of binomials, and so on. And more trivially, just by looking at operators or by computing the 2-point function, this guy has dimension, which is 2, 1 from each scalar, plus s from all the derivatives, so it has dimension s plus 2. Or twist, which is defined as the difference between delta and s to be equal to 2. And another comment is that if we were to use phi and phi instead of phi and phi bar, of course such terms, for example, are 0 immediately, because I mean you have phi d phi minus d phi phi, so it will be 0. So this kind, then only even spins would exist. Okay, and just one other comment, that it's useful when you deal with symmetric traceless tensors. To get rid of the indices, you can contract them without losing information with null vectors. And in other words, you can, instead of having all these indices, just choose some null direction and consider k derivatives in some null direction and s minus k derivatives in that null direction. And this is a nice component of your symmetric traceless tensor. Okay, very good. So this is just a few comments about what you have seen. I just want to summarize, because some of you might not have done the homework or something. And this is what you have studied. Now, back to what we were doing last time. So we were seeing that we can have a gravitational box, and we can have a theory of quantum gravity in this gravity box, which is AdS 5 times S5, whose boundary is a cylinder, R times S3. And we have a duality between strings in AdS 5 times S5 inside this box and the conformal field theory that lives on this boundary 4-dimensional cylinder. And more than just some hand-waving words, we had a precise formula that energies of strings moving on that box is equal to the energies of strings of states at the boundary on the cylinder, which are equal to the dimensions of operators in your conformal field theory, which is n equals 4 super Young Mills. Okay. Any questions so far? Okay. So now, the plan for today is to start learning a bit more about n equals 4 super Young Mills and to try to compute some anomalous dimensions in n equals 4 super Young Mills. Okay? So today's goal is to compute some data on the right-hand side here. Okay? Now, n equals 4 super Young Mills describes the low energy dynamics of open strings subject to living in a D3 brane. Right? So it's open strings that live in 4 dimensions. 3 plus 1. So a simple way of understanding n equals 4 super Young Mills in 4 dimensions, you can think of it as coming from the low energy description of open strings in 10 dimensions, which is given by n equals 1 super Young Mills in 10 dimensions, compactified, that is, you say that the fields don't depend on the extra 6 dimensions, compactified to 4 dimensions. Okay? So this is the low energy description of open strings in 10 dimensions, and you restrict to 4 dimensions to get the effective description on the D3 brane. So, of course, immediately just from this blah blah, we get here, we get a 4D theory that smells or that resembles, I don't know, that has a 10D flavor. There are some elements in this theory that remind us that it is naturally described as coming from a reduction from 10 dimensions. There are some things that might look a bit strange, but they become very natural once we remind ourselves that this is its original origin. So this theory is very simple. This n equals 1 theory in 10 dimensions is very simple. It is just given by the integral in 10 dimensions, okay, of the trace of just Young Mills, okay, plus some fermions. Okay, that's it. You have some gauge field and you have some fermions. And there is a supersymmetry transformation that rotates the fermions into the gauge fields and the gauge fields into the fermions. So have you encountered a little bit of supersymmetry already? Yes? So, okay. So you have seen that there are such actions which have some supersymmetry between the fermions and the gluons, right? Yes, this is the simplest one. Very good. So now let me reduce this action to form 10 dimensions, and let's reduce it to 4 dimensions and see what happens. Okay? But maybe, just to make sure that everyone understands what we are talking about, I just find it often useful to just make sure we understand all the indices involved in this expression. Okay? So let's maybe write this out very explicitly just to make sure that everyone is following. Okay? So what do we have? What does this mean? This means that we have some psi bar. Let me write here some psi bar. Then we have some gamma matrix, some derivative of psi, plus I, some commutator of the gauge field with psi. Okay? Is it okay? So now let's put here all the indices that these guys should have just to make sure we understand. So all these fields, they are n by n matrices. They are all in the adjoint. So all these fields are matrices. So this is an n by n matrix. It has some indices. So, okay, let me first start by another index. So this is a spinner. So there is a spinner index. So we can put here some b. And this b is a spinner index. And here we have a. And we have our gamma matrix, gamma AB. And we sum over A and B from 1 to 16. So these fermions, they are 16 component real fermions. So these are Majorana Weil spinners. Okay? So it's 16 component real spinner. So it's a fermion. So you know that fermions, the number of degrees of freedom is half, right? Because half are momenta and half are coordinates. So we have 8 degrees of freedom. Is it okay? And how many degrees of freedom do we have for a 10-dimensional gluon? Well, 2 degrees of freedom are not physical, so we have 8. So we have the same number of fermionic and bosonic degrees of freedom as we need to have supersymmetry. Okay? Is it okay? So 16-dimensional real spinner has 8 degrees of freedom. 10-dimensional gluons, you have 10 minus 2 degrees of freedom. So it's good. So it has supersymmetry. So we have some spinner index. There is some derivative that is in some direction m. And A has some index m. So we sum over m. M you sum from 0 to 9. These are the dimensions of space-time. Very good. What else are we missing? Well, these guys, as we said, they are matrices. So they have some indices A, B. And again, these are matrices. So here there are some indices B, A. I put the same on the first and on the last because there is a trace. And you sum over A and B. That runs from 1 to the number of colors n that we send to infinity. Okay? Similar for the gauge field. Okay. So now, next, we drop the dependence on this 6-dimensional coordinates on x4 up to x9. So our fields only depend on x0 up to x3, the 4 dimensions on the brane. So let's see what happens. Let's first start with F and M, F and M. Well, let's see. So these indices, they can both be in the 0 to 3 direction. In that case, we get F mu nu, F mu nu. So what we are doing is we separate this index M, which goes from 0 to 9, into some index mu that runs from 0 to 3. We use mu and nu for this kind of indices. And then some index I that runs from 1 to 6, which was before M running from 4 to 9. Okay, so we shift a bit, and we use I and J for this kind of indices. So this describes the 6 dimensions that we are compactifying, and this describes the dimensions that we are keeping. So if both indices are there, then we get the usual F mu nu, F mu nu. Then we can have one index in the first 3 components and one in the last ones. And then we get the following. Let me just write the full result, and I think it will be clear. And we separate our gauge field AM into some A mu and some scalars phi I. And then we have d mu phi I d mu phi I plus commutator of phi I, phi j, phi I, phi j. So what's happening here? What's happening is that we have these covariant derivatives. They have all these commutators inside. But you see that when we expand this out, there are no derivatives with respect to I, because those directions, the fields don't depend on them. So the terms that would correspond to f mu I will just give you these things. And the terms that would correspond to f I j, the derivatives drop completely, and you only keep the commutators from the covariant derivatives, and you generate some interaction term. Okay, is it clear? This is just what you get if you just use this gauge field and say that these guys only depend on x0 up to x3, but they don't depend on x4 up to x9. Is it okay? Okay, so that's fine. And then you can have your psi bar d slash psi, and this would be psi bar gamma mu d mu psi plus commutator of a mu with psi. This is if the index that you sum over here, m, will be in the direction mu. If it's not, it just is plus psi bar gamma I commutator of phi I with psi. Right? Because if the index is I, there's no di, so you only get the commutator. So it generates a Yukawa interaction between the fermions and the scalars. Okay, so the sum of these two terms was just n equals 1 Lagrangian. And if you sum all these terms, this is the Lagrangian of n equals 4 super Young-Mills. So this is just a mnemonic to remember all the terms in case you forget. But this could be our starting point. So you see that n equals 4 super Young-Mills. You can think of it. It contains the usual interesting term that we all would love to study by itself, QCD. And then it has some matter fields with some scalars and some fermions and so on top of that. Okay? So this is just the usual, the Lagrangian of pure glue plus some matter. Okay? But not any matter. It's a special matter such that the full Lagrangian has this maximal supersymmetry, which is n equals 4 super Young. Okay, very good. What else do I want to comment? I want to say that all fields are in the adjoint. That is, they transform as in under a gauge transformation as chi under a gauge transformation goes any field, any of these fields here. This chi can be a scalar, a fermion, a gauge field, a covariant derivative of a fermion, whatever. A field transforms under a gauge transformation as a field plus commutator of epsilon with a field. Okay. Of course, the connection A mu is not a gauge invariant operator. It does not transform in this way. Let me just write for the connection. A mu goes, as usual, to A mu plus d mu epsilon plus commutator of epsilon with A mu. But if you construct a gauge invariant operators transform in this way. Or equivalently, a finite transformation, chi goes to u, chi u minus 1. At a given point in space. Okay. So what are local gauge invariant operators? So if this is how a field transforms under a gauge transformation, how can I construct gauge invariant operators? How can we construct an operator that is invariant under gauge transformation? Right? So what could be another? I mean, a field by itself is not a good observable. It's not invariant under a gauge transformation. So how can I construct something that is gauge invariant if the field transforms as u times u minus 1? Any idea? Sorry? Trace, right? So if I construct a product of fields, let me construct a product field, chi1 at some point x, chi2 at the same point x, all at the same position, chi-l at some point x. So all at the same position, exactly like our composite operators that we saw in the homework. Then if we transform under a gauge transformation, all the u's in the middle cancel out, u minus 1 u is equal to identity. And we would get a u at the beginning and a u at the end. So if we take a trace, this is a local gauge invariant operator. These guys, as we saw before, these nice operators, they are the dual of single string states. And I remind you that we have large N factorization. So these are the fundamental building blocks, a correlation function of several of these guys to leading order decouple, and the most interesting part is the dimension of these operators, and so on. Well, another important comment is about, so all this action, okay, I should write slightly different. The Lagrangian of n equals 4 super Young-Mills is whatever you get by summing all these terms, and there is a coupling, 1 over G Young-Mills square. And now you can ask, what is the beta function? What is the beta function for this coupling G Young-Mills? So if you have some scale, how does the coupling change as you change your energy scale? Now, in any theory where your fields are in the adjoint, at one loop, so this is what it is. So can you anticipate what will be the answer to this question? Based on the fact that, but people that, I mean, did not work on n equals 4 before. And someone, didn't you work on n equals 4? But you are working on n equals 4, right? Okay. Very good. Okay. Anyway, it is 0. Why it is 0? Why should it be 0? Yes? Exactly. Because it should be scale invariant. It should not depend on the scale where we are. We are tired of saying this is a CFT, this is a CFT, this is a CFT. So by definition, a CFT, a beta function is 0. So this should be 0 to all orders. Okay? So indeed, the beta function is equal to 0 at any coupling. And it has been shown by several arguments, the most powerful of which use supersymmetry, but there are several arguments to show that the beta function should be 0 to all orders. But let me just remind you how easy it is to see that it is 0, say, at one loop, for example. So at one loop, we know how to compute the beta function for any theory that has a given matter content. So the beta function at one loop, for field, when all the fields are in the adjoint, it's very simple. There is minus G Young-Mills cube over 16 pi square. And then there is the famous 11/3 of QCD, right, with minus signs, very important. And then minus 1/6 times the number of scalars, which are 6. So this is times n. Number of scalars. Okay. Minus 2/3. And then what enters here, this 4, okay, is the number of wild fermions. And now this one you have to trust me that if you reduce the Majorana wild fermion in 10 dimensions, you get 4 wild fermions in 4 dimensions. But you can count degrees of freedom and check that a wild fermion has 2 degrees of freedom. So if you put a 4 here, you get 8, which is the same 8 that you got before. Right? Fermion in 4 dimensions is an electron. It has 4. And then the wild fermion has 2 degrees of freedom. So you get again the number of degrees of freedom we started with. And if you compute this, if I did no mistake, this is equal to 0. Okay. So it is just a one-line computation. If you know, of course, this general formula. You can find this formula, for example, in Peskin. He computes by background field method what's the beta function. Okay, but this is just at one loop, but this general statement that this is true at any loop order, which is, of course, directly related to the important but worth stating that n equals 4 super Young-Mills is a conformal field theory. Okay. By the way, as I said before, the beta function of this theory, you see that the beta function is derivative of G Young-Mills square. Okay, derivative of G Young-Mills, the way I defined it. Derivative of G Young-Mills with respect to the coupling. Here you get G Young-Mills squares cubed times n. You might ask, if I want to take n to infinity and have something held fixed, what should I do? And it's easy to see that if you compute the beta function for G square, then you would realize that what you should hold fixed is lambda, the 't Hooft coupling. So if you want, it's another way of arguing for the 't Hooft expansion limit. Okay? So if you want to keep lambda QCD fixed, when taking n to infinity, you should take the 't Hooft limit. Okay, very good. Now that we know the theory, okay, we can start computing. And the goal is now, so the goal is to compute some deltas. Okay? Well, we already have some deltas here. S plus 2. And there is an analog of these operators that you can construct in n equals 4. You have 2 scalars. So you could imagine an analog of these spin operators. Okay? An analog of an operator with spin. For example, one operator we could consider is an operator with spin S, which would be a trace of some field. I will introduce some new notation. Let me explain in a minute what this is. Z. So this Z will be a complex scalar. And we can have some derivatives, k derivatives acting on it, and S minus k derivative acting on Z with some coefficient ck. Okay? Very much the analog of these operators with spin that we considered. That would be one example of an operator that we could consider. For example, this Z is a complex scalar that you can construct. So you can define Z to be phi 1 plus I phi 2, X to be phi 3 plus I phi 4, and say Y to be phi 5 plus I phi 6. And similarly, it's complex conjugate scalars. So I remind you, there are 6 scalars. And you can construct out of them some complex scalars, just because it's a bit convenient. And then you could try to construct this operator. And then we can ask, what is the dimension of this operator? Well, the dimension of this operator, it's S plus 2 as before, of course, plus quantum corrections. Okay, because if this was just a free theory, this was all there was. But now we have a quantum theory. To leading order, if you just do weak contractions, I mean, this problem is combinatorically very similar to that one. And I mean, to leading order, you just count how many derivatives and how many fields you have. So the dimension is clearly S plus 2. What about quantum corrections? How can you, for example, they would generate these quantum corrections will be a function of the coupling, the 't Hooft coupling, lambda. Okay. So if we plot this dimension, the idea is that this is the coupling lambda. This is the dimension. They start at s plus 2, and then they go to something, and then they go to something, and this is where string theory will naturally make some prediction for how they behave. This is where perturbative Yang-Mills will give a prediction, and then the claim is that the two curves, if we were able to compute it many powers of the many quantum corrections at weak and strong coupling, we would see that the curves would match perfectly, and this would be the statement of AdS CFT. So our goal, for example, is to take some operators and compute this beginning of this curve of dimensions as function of lambda. Is it clear? Okay, let's do it. And I will actually consider exactly these operators here, just for illustration. Okay? By the way, you can easily convince yourself by the same argument that this CKs should be exactly the same as before. Because you can again repeat the same exercise. Start by just, so this would be exactly this CK. They will not change. And why not? Because you can start with trace of z squared, which is the primary, and then repeat the same argument. Just one derivative of the primary, or put the derivative in the middle, and so on. And you would conclude that it ought to be exactly the same kind of linear combination. Is it clear? Yeah? Okay, very good. So we want to study the quantum dimensions of this operator as an illustration of this method. So there are two ways now of computing. One way of computing is computing the dimensions directly. I mean, how do we read the dimensions? By studying two-point functions. We compute two-point functions at loop level, and we read what the dimension is. Okay? What is the other option for computing the dimension that we encountered already in the lecture? That I told you that there would be another method of reading CFT data. I don't want to consider correlation functions involving these guys. And I want to read their dimensions without ever considering a correlation function that involves these guys as external guys. So how can I do it? I don't put them as external guys. Any proposal? So we are going to compute some lambdas. The second way is computing this directly. And by directly, I mean we will relate deltas to the renormalization of operators. This you have seen, right? That renormalization of operators and the critical exponents are directly related, right? So if you study renormalization, the way you multiplicatively renormalize an operator is directly related to the dimension of the operator. But I will remind you of this statement. But you have encountered it before, right? Probably in John Berlinski's course, for example, I'm sure. You relate the renormalization and the study of the RG and the behavior close to the RG to the anomalous dimensions of operators. But I will remind you of this in case you forgot, or in case you did not see it before. And the second way we are going to compute it is we are going to use a simple 4-point function. And we are going, remind that in the 4-point function, we can consider some very simple operators here. They can be all the same or they can be different, doesn't matter. And the complicated guys appear because we have to sum over everyone, over all the operators with some dimension and some spin. So by studying a simple 4-point function, these complicated guys, they will be somewhere in the middle. And by analyzing the 4-point function, we can read what their dimension and what their spin is. Okay? So just by studying a more general process that computes all these guys at the same time. Okay? So we use a simple 4-point function, and from this computation, we read the 3-point functions immediately, 1 to k, and the dimensions delta k that are flowing. Okay, so let's do both. Hopefully today I can finish the first one, and tomorrow I'll explain you the second one. Okay. So let me tell you what operators I'm going to consider. I'm going to consider the following operators made out of complex scalars. O1 equal trace of x, z. O2 equal trace of x bar, z. O3 equal trace of y, z bar. O4 equal trace of y bar, z bar. Now, let me first of all emphasize that many correlation, I could consider many options. Provided these operators are produced in the middle and flow, I can consider any external data that contains some overlap with the operators I'm interested in, and this would be enough to read their dimensions. I'm going to consider these ones because of several reasons. First of all, these are very simple operators. Okay, they are very small composite operators just with two fields. They all have zero anomalous dimension. Okay, so they all have dimension equal to 2 exactly. Okay, so there are no quantum corrections. And this is basically because of supersymmetry. And this will become more clear from the second point of view that we will see tomorrow. For now, just believe me that these operators have dimension 2 and nothing else. They are what's called BPS operators in the gauge theory. Protected operators. Okay? This is one reason. Okay. And then we consider this correlation function. Okay? So let's draw this correlation function. So let's compute this correlation function, G4, which is the correlation function of 4 guys, O1, O2, O3, O4. And we are going to take the OPE between these guys and these guys. Okay? So we are going to write this as an OPE where you have some dimensions being exchanged, 1 and 2. If I write L, please correct me, because in this lecture apparently I'm using S for spin, but somehow I use always L when I'm doing conformal bootstrap and S when I'm doing the second approach. I don't know why, it's psychological. So please correct me. L should always be S, and I'm sure I will write it a few more times as L. Okay. So what is this correlation function? Let's consider it at 3 level. Okay? So at 3 level, what do we have? So we have the propagators. Our propagators, what are our propagators? Between a field phi I and phi j, they are equal. Okay, the scalars need to be equal, delta ij, over x minus y squared. Okay? I'm only worried about the space dependence. I'm not worried about n. I'm ignoring n. N from the pictures we read off powers of n. I'm just writing the space dependent. Now, this is just because the kinetic term is diagonal. Now, if you go to this complex scalar, you read off that the correlation function between a z and a z is equal to 0. A z bar and a z bar is equal to 0. And the one that is not 0 is a z with a z bar. That gives 1 over x minus y squared. And similarly for the other fields. And also z with x is equal to 0, etc. So please tell me, do you agree that z with x and so on equals 0? It's obvious, because z contains scalars phi 1, phi 2, and the x contains different scalars, so of course it follows immediately from this. That's clear, right? Is it clear that z and x have 0 overlap? That z and z have 0, maybe it's not totally obvious, but it's also clear, because if you remind, this is phi 1 plus I phi 2. This is again phi 1 plus I phi 2. So only the phi 1 with phi 1 and phi 2 with phi 2 matters, but because of that I, they contribute to the opposite sign and you get 0. In other words, out of a real scalar, you construct the complex scalar, but now you have a U1 symmetry that rotates z and z bar. That's a symmetry of your theory. So it's like your scalars are charged and you cannot destroy charge. Okay? So your fields now have an arrow if you want. Z going to z bar. Okay? Okay, very good. So then it means that the diagrams that come from this kind of operator are very simple. Z's must go to Z bars, Y to Y bar, and X to X bar. Okay? So it's very simple. If this is operator 1, 1 is an operator that, let's write in double line notation. This would be 3. Two and 4. Now operator 1 has a Z and an X. The X field must be contracted with X bar of operator 2. The operator 2 has a Z. These Z's must be contracted with Z bar, and here Y bar, Y. Is it clear? This is the diagram you can write. There is one more diagram. Which one? Can someone tell me what other diagram you could draw? So first of all, between 1 and 2, the only weak contraction, the X must go to the X bar. There's no option, right? Between 3 and 4, the Y must go to the Y bar. There's no option there, right? But what you have the option is that you can connect this guy to this one, and then this line to this one, right? So you can exchange 4 and 3. It's clear? So plus the same thing with 3 and 4 exchanged. Okay, so let's write what we get. Well, I remind you that to write a 4-point function, it's very useful to take out a space dependence. And if all the operators have the same space dependence, the dependence we said we should take out is x1 minus x2, x3 minus x4 square, all these to the power of their dimension, which is 2. I remind you, this was the factor that we took out. And now, whatever we are going to write here, this will be just a function of the cross ratio Z and Z bar, unless we are doing some mistake. So this is a good check of what we are going to do, right? So I remind you, external operators dimension 2, they have an overall factor, and then what multiplies is a function of Z and Z bar. So what is it? Let's look at this diagram here. Please have a look. So I wrote 2 propagators here, but there's only one propagator. There's only one propagator between 1 and 2, and one propagator between 3 and 4. I wrote too many propagators. I have to put a factor upstairs here to cancel one of them. x1 minus x2 square, x3 minus x4 square. So that's just because I only have one propagator here and one propagator here. And then I have a propagator between 1 and 3 and one between 3 and 4. So I have here x1 minus x3 square and the other one x2 minus x4 square. So this is the first diagram. And the second diagram, you exchange 3 and 4. So let's exchange 3 and 4. The top part is invariant, and the bottom part you get x1 minus x4 square, x2 minus x3 square. Indeed, it is exactly a function of cross ratios. Okay? So everything is coming out correctly, as we said should. Now, if you look at your notes, this was exactly what we had defined as U, the cross ratio U. And this one is nothing but U over V. And the relation between U and V and the convenient Z and Z bar was that U was equal to Z, Z bar, and V was equal to 1 minus Z, 1 minus Z bar. And this was useful because the conformal blocks were looked much more nicely in terms of the Z and Z bar than U and V. So these are kind of more convenient. Okay? Very good. Let's continue. Okay, so we computed this function at 3 levels, f z bar, okay, at leading order. It's equal to, well, it is just that it's u, which is z times z bar, times 1 plus 1 over v, and 1 over v is 1 minus z bar. Okay? Very simple function of z and z bar. Okay? What is the claim? I remind. The claim was that this function, on the other hand, at any loop order, the idea was that this f, z, and z bar should be equal to a sum of a 3-point function between operator O1, O2, and the operator that is being exchanged, times the 3-point function of the operator that is being exchanged with O3, O4. Okay, and this guy has dimension delta and spin s, times a function f that depends on delta and s and z bar. And this function was the conformal block and this function was just given by z times z bar over z minus z bar, some function h of z, h of z bar minus z being exchanged with z bar, where this h was just some hypergeometric function of z. Okay, very good. And this was the form of conformal blocks in 4 dimensions. Okay? So these functions, okay, okay, very good. Any question here?
L is S. Yeah.
Again, yes, as I told you, L is S. Yeah. Yeah, I don't know, it's really strange. I can't explain it. Very good. Yeah, delta is S. Okay, very good. Now, these functions, okay, these guys are more suppressed at z bar goes to 0, which I remind you is the OP limit, for large dimensions. So these have a power expansion that starts higher and higher as you exchange higher and higher dimension operators. Okay? So all you do is you expand at z bar going to 0, and you expand in this base of functions. Okay? So you look like the term that decays the slowest, which is just, you just ignore these terms and it goes like the z bar. And z bar, which hypergeometric starts only with z bar? Which conformal block starts only with z bar? And you can easily see which one it is, and you subtract it out from your expansion. Then you look at the next power. You see what you need to put, and you subtract out. And you do it in this way, term by term in your expansion, fixing the first 100 terms until you already get that this minus this only starts at z times z bar from power 100. And you continue to do it more and more and more until you find some pattern, and you just see what constants you need to put and what f's do you need to sum over. Is it clear? Yes? So if you have an expansion of a polynomial expansion in z and z bar with some polynomials, and those polynomials start at some given power of z, right? You look at the lowest order of your polynomial, the one that just has z, and you see which polynomial just starts with z. And I subtract that polynomial. Now there's no z, there is z squared. I look at z squared. Which polynomial starts with z squared? I find that, I subtract it. Now there's no z squared. I look to z cubed, and so on. Of course, I have to do it one by one, because after subtracting the polynomial that killed z, I changed the coefficient of z squared. And now I do z squared by subtracting z squared, I change the coefficient of z cubed. I do z cubed, I subtract, I change coefficient of z to the 4, and so on. So it's very simple to do it. You just do it in Mathematica. I did it yesterday night. It's really very simple. Just expand and start subtracting. And the pattern starts to be very clear. And I leave it as a check for you, a very simple check to do that. If you use those functions, this function at 3 level, this f z bar at 3 level is nothing but the following. It's the sum over s. It's given by the following sum over s. And then there is square root of 2 s factorial over square root of 2s factorial square times hypergeometric s plus 2, no, not hypergeometric, conformal block, s plus 2, comma s of z and z bar. Okay, this is an identity. This simple function, this is the nicest way of writing a simple function in the most complicated way using hypergeometric functions. So your result couldn't be simpler. And now you decided to write it as an expansion in hypergeometric functions like this, which you can, of course, do. Very good. But now we see the beauty of doing this computation. It's a very straightforward computation. What is it telling you? It's telling you that the dimensions of these guys is s plus 2. And this here is telling you what is the 3-point function between the operator O1, O2, and the operator with that delta and that spin. And it's the same for 3, 4, and that's why we have a square. And this result here and these results here, they match exactly what you would compute by a painful direct computation. Right? So you see, it's a very nice way, just by computing a 4-point function, expanding it in the right base of functions, looking at the coefficients. This is the only thing you have to do. In Mathematica, what you do is you generate a table of these numbers. And then you start seeing some numbers. 1, 3, 5, 1 over 7, 1 over 27, blah, blah. You get like 100 numbers. And then you start seeing some patterns. You start seeing, okay, if I divide by s factorial and so on, you can easily see that these numbers, first you see that they are always a square, so you take a square root, and then they are still rational numbers. Then you see that, well, you play a bit, and you have some guess for what it should be, and it's easy to guess. So it's a nice check you can really do. I actually don't know how to prove analytically that you sum these hypergeometrics and you get just that. But I'm sure it should be simple to do. But what you can do is just plug this expression with these hypergeometrics, tell Mathematica to series expand this up to order 200 and check that this matches the expanding that function there in z bar small up to order 200, for example. Okay, very good. But this was a 3-level computation, and it only told us about what we knew already. The dimensions at 3 level, and it showed us that this was a nice way of reproducing the structure constants. But what we wanted was to understand what's the quantum corrections to this formula. Well, but now it's simple. What we should do is ask someone to compute a 4-point function at 1 loop and repeat this analysis. This is not a very tough computation. It's just this 4-point function. Now you start decorating it by loops. Okay, so I started 5 minutes later, so I still have 7 minutes, but I think I need probably 12. So we will end 5 minutes over time today, but I will finish the 1-loop computation. Unless you prefer to stop here. No, you don't. Very good. So let's do the 1-loop computation. Is it clear so far? So we have to do the 1-loop computation. So the 1-loop computation, what do we have to do? I'm not going to do, but just tell you what kind of stuff you would have to do. So by this, for example, I represent the gluon being exchanged using fat line notation. So this is an example of a graph you would have to compute. Now you have your operator 1, 2, 3, 4, plus, and these are the kind of graphs you have to compute. Okay, but you do it, and it's actually not very hard, even though I never did it, but it's easy to do. And what you get is some function f of z and z bar at one loop now. And that function is quite simple. It's the following. There is a rational prefactor. So there is, first of all, some lambda over pi square. I should say that in this blackboard, I'm setting 2 equal minus 1 equal pi equal 1. Yeah, just, this is all up to 2s and stuff like this that I didn't keep track of. Yesterday there was a minus that I couldn't get rid of, so I don't care. And then there is 1 minus v minus u times u over v minus 1 minus v plus u times u. This is the rational part that you get. Okay, some very simple function. And then you compute the interesting part is this phi that is here. That is the interesting part that depends on z and z bar. This, of course, also is the function of z and z bar. I just wrote it in terms of u and z. And this phi is equal to 1 over z minus z bar times 2 Le2 of z minus 2 Le2 of z bar plus log of z bar times log 1 minus z over 1 minus z bar. Okay. Does someone know what an Le2 is? The polylog. Is it familiar to everyone? Yeah? Not actual? Okay, so let me just, a polylog, one way of defining a polylog function, Lin of z, you can define it by its series expansion. It's a sum z to the k over k to the n. Okay? So you see that, for example, Li1 of z is just our famous log. Okay? But Li2, it's a new function. Okay. But already from this definition, you see something. So these guys, Li, they have a regular expansion around z bar equals 0. This function also had a regular expansion around z bar equals 0. Right? You expand in z bar, you get some Taylor expansion. This guy also has a regular expansion, but this guy is a log. Right? When z goes to z bar, everything has a regular expansion except some very precise part of the result that we identify there that comes multiplied by log of z bar. How could we get logs? How could we start getting logs from this OP expansion, where we said we get just poles with the anomalous with the dimension of the operators and so on? Where are logs coming from? Any proposal? How could we imagine generating logs? Well, this hypergeometric has also a regular expansion. But this guy here, it's kind of different. What happens is that when you are expanding this f, delta, and s, you get an expansion where this guy, because of this power here, contains some power, z bar, okay, to the power delta, or maybe delta over 2, I don't know, times some regular expansion. Now, this factor here is regular. It's just a simple power of z if this delta is an integer, if it's a number. Right? If it's 2 or 4 or 6, even if it is half integer, it's okay. It's z bar some power, half integer power. It's not a singularity. Is it okay? But suppose we are doing perturbation theory. If you are doing perturbation theory, then when you have z times z bar to the power delta over 2, this is equal to z times z bar to the power delta classical over 2 plus some gamma, where gamma is the anomalous part, and it starts at lambda times some 1 loop correction plus lambda square times some 2 loop correction plus etc. etc. So when you expand this in perturbation theory, you get z bar times some delta classical, maybe over 2, I don't know. And then you get 1 plus gamma over 2 log z bar plus tac, tac, tac. Okay? So it's perfect. It's perfect in the sense that the logs can only come from here. It can only come because what we are expanding is some anomalous part, and when you expand in this anomalous part, the only way you can generate logs, they come immediately multiplied by the quantum correction that we want. Okay? So the log z bar contribution in this f z bar 1 loop is directly related to this anomalous, to the fact that the dimensions get some anomalous contribution. If they did not get an anomalous contribution, no logs could ever appear. The fact that we start seeing logs at loops, it's the effect that operators get anomalous dimensions. It's really one-to-one. Is it clear? Okay, very good. So in other words, let me summarize. So if you have the 1 loop result, there are 2 sources of loop corrections. One source of loop corrections is you can correct your 3-point functions. You can correct your probability of creating a particle in the middle. Okay? And then you don't touch the dimensions of your operators. That stuff can never generate logs. So that stuff must be related to the first part here. Or you can correct only the dimensions of the operators, and then this should be what this part is. So this part of the result here, we call this phi log part, is what we need. Okay? Very good. So we expand that. And when you expand that, you get the following. You get that f, if you just keep the log part, the part that is proportional explicitly to log z times log z bar, okay, is equal to log z bar times the following, times the sum over s. And then you get the same thing you got before, square root of 2 s factorial, square root of 2s factorial, times here 2 lambda over pi square, sum from k equal 1 up to s 1 over k. This is some new contribution, times the same hypergeometric function f, s plus 2 comma s of z and z bar. This is what we call a twist 2, the contribution of the states with twist 2, plus there is a similar contribution from a new type of states that appears, which are the twist 4 states. But they come with an hypergeometric f. This is a sum that contains f, s plus 4 comma s, so we don't look at it because we are interested in the twist 2 guys. Okay? Is it clear? This is again just expanding that log part. So by looking at this, we identify this part as being exactly the anomalous dimension of the operator with spin s. Okay? So the conclusion from this analysis is that the dimension of the operator being exchanged, which is the twist 2 primary, is equal to S plus 2 plus a correction, which is 2 lambda over pi square times what's called an harmonic number of S, where H of S is defined as the sum k equal 1 up to S 1 over k. Plus order lambda square. Now, did we use all the information we could get from the 4-point function? Far from it. Not at all. For example, now we could go to the part that has no log and study what is the correction to the 3-point function. You see, what we got here, square, sorry, this was just the 3-point function at 3 level, square, but we could analyze now the terms that come with no log and study what's the one loop correction to the 3-point function. Right? But okay, since we wanted to study only dimensions, we looked immediately at the part that was interesting. Now we only have to expand this very simple function of ZZ bar, this 1 times whatever rational factor multiplies. It's not much more complicated than the exercise we did before. We do this exercise, and this turns out to be what we find. Again, you would get a table of numbers. Because you know that these numbers are the 3-point function times some anomalous dimension, you divide that table of numbers by this. So you get rid of this, you would get this, and you would only have to guess what this is, and you immediately fit it with these harmonic numbers. Plus order lambda square. Okay? So this is our first computation of an anomalous dimension in a conformal field theory. This is the first one loop quantum correction. Then there are 2 loops. Then there are 3 loops. So now we can draw the beginning of that plot. So indeed, it starts at S plus 2. Then it goes up. It's a positive number, so it's a lambda. So the plot that I drew at some point was indeed reasonable. It's probably hidden behind this, right? Indeed, this is a reasonable plot. We start at some S plus 2, we go up. And indeed, we will see that in string theory, we are indeed up there and we come down. So this would be the correction from string theory. So we will see that the beginning and the end parts of the plot are indeed at least going in the right directions, and we are just computing its very beginning. Okay, let me just make one comment, which is that you see how easy it is to use this conformal bootstrap method to extract anomalous dimension 3-point functions. But there are two things that we should keep in mind that are obvious limitations of this method. One is that this was particularly powerful to compute a particular 3-point function and a particular dimension because there was no degeneracy. Because there was a unique operator. As soon as you have twist 2, you knew who are you speaking about. As soon as you have, say, twist 4, there are many operators now that you can write. I mean, you have a degeneracy. There are many ways of putting the derivatives. You have more than one primary. So what you are getting from this method is not a 3-point function only, but a sum of 3-point functions. Okay? And that's okay. And you don't get immediately one anomalous dimension, but you get a sum of anomalous dimension weighted by the 3-point function. Okay? This is one thing. So if you would like then to isolate 3-point functions, you could play with having more than one correlation function and so on. You could play some games to try to isolate from that data the contribution of a single dimension. Okay, that's one comment. The second comment is that what we see here is that there is a very nice separation between the terms that have a regular expansion and the terms that have some logs. Okay? And now you could imagine, what about 2 loops? What could happen at 2 loops? You see, without doing any computation at 2 loops, you can immediately predict what should happen. What should be the structure? There should be some terms with rational expansion, some terms with log ZZ bar times rational expansion, and some terms with log ZZ bar squared times rational expansion. Why? Why can we have now a log square singularity? Because when we expand z times z bar, we can now expand it to quadratic order. Right? We were expanding this z times z bar here. We can now take the second term here. That will be some gamma square over 8 log square of z bar. But this term here, because lambda starts at 1 loop, this is a 2-loop effect. Okay? But you see that this is a 2-loop effect that if you want to see it at 2 loops, the anomalous dimension that you put here, because you have square, you put the one loop energy that you computed already. Right? Is it clear? So you can predict what should be the behavior as log ZZ, what should multiply log ZZ bar square. What should it be? It should be given by exactly this function here, where you put the square here. Right? If you put a square here and the square here, this is the prediction for the log square part at 2 loops. Right? Without any work, you could immediately predict what it should be. You see? So this idea, it's an idea that appears in many places in physics. It's what's called the leading log resummation. It often happens that you have some part of the result that you can resum using some lower loop result and understand very well how to resum it and to get information at any loop. Here it was the most singular behavior as Z and Z bar approach each other. This gives this log to some power that at L loops can be at most log ZZ bar to the power L. And the highest power, the highest singularity, we can predict already just based on resumming this one loop result. You just dress the bare 3-point function by the anomalous dimension at one loop to some power L. Similar ideas happen everywhere in physics. In high energy scattering, sometimes you have some exchange and you just exponentiate that exchange. In recent computation of Wilson loops, people understood how to use some similar OP techniques. So this is a method that is very, very powerful and that can help constrain a lot higher loop results. If someone gives you now the 4-point function at 2 loops, you can immediately say, let me see if this, you can already pass some consistency checks. The log square term cannot be whatever they write. You can immediately check, is it consistent or not with what we are seeing already? Similarly, if you have a guess for what a 2-loop result is, say, imagine you have a guess, and you say, it's the sum of these 3 functions, but I don't know exactly the coefficients. Maybe you can fix them by imposing that you get a good behavior as ZZ bar goes to 0. And this is indeed the kind of games that people play a lot in studying very high loop computations. They know some constraints from these resummations. They have some guess for the set of functions that could appear. And often this is the kind of things they use because often Feynman diagrams is just way too hard to do. Okay? Finally, the last comment I want to make is about this ZZ bar to some power, and then it multiplies some regular expansion, this conformal blocks here. This again has some physics. It's not just a technical mathematical observation. What are we seeing here? We are seeing that as ZZ bar goes to 0, the conformal block gives ZZ bar to some number, which is some number that doesn't need to be an integer. It's whatever it is. It's related to the dimension of the primary. But what does the conformal do? Remember, it sums the primary plus all its descendants. But all the descendants of the primary just differ by the primary by some integer power. Right? Because the energy of the descendants is the energy of the primer plus some integer. So this is why the conformal block, they have this structure. They are Z times Z bar to some power, which can be whatever it is, times some rational expansion, some regular expansion in ZZ bar, such that each term in that expansion is related to one particular descendant. Is it clear? Is it clear? That it should be like this, ZZ bar to some anomalous power times a regular expansion. That it starts at 1, which is the primary, plus, say, Z, which is the first descendant, plus Z squared, second descendant. That contribute to some exponent, which is delta plus 1, delta plus 2, delta plus 3. So you can have powers that are not integer, but they must differ from the primary just by an integer. So once you divide by the primary, it should have a regular expansion. Okay, very good. So tomorrow, in the lecture and then in the exercise, we will reproduce this result by a direct computation. Totally different point of view, and of course, we will get the same. Okay. Questions? I would rather not revisit this tomorrow because, I mean, what I'm going to do tomorrow is really totally independent. So if there are questions about this, it would be really great if you could ask now. I'm not planning on summarizing this computation here. I thought this is self-contained. It's related to what we saw before. It doesn't fit nicely tomorrow, so please ask if you have any questions. No? Looks good. Okay, see you tomorrow then.